CE366 Geotechnical Engineering 1, Lecture 3, Soil Hydraulics, Part 1, Permeability. In this lecture, we'll try to achieve three learning objectives. First, at the end of the lecture, students will be able to calculate three different heads: total heads, elevation heads, and potential heads. Second objective, students will be able to know more about Darcy Law. Finally, at the end of the lecture, students were able to find the coefficients of hydraulic conductivities in both isotropic and anisotropic conditions. Introductions. The groundwater flow is what we try to learn more about in this lecture. And we need to characterize our water flow within our groundwater systems. And some key points here is, first, we emphasize the directions of flow of the water is from the high energy to low energy point. Second, what we learned in this course of this lecture about soil hydraulics is we restrict the water flows to be static flow only. Also, we only look at 1D conditions. For the velocity of water, we assume is laminar. For the density of water, we assume it is incompressible. So this is a Geotech 101 class, and it's not kind of like a water resources or focus on groundwater flow. So we pretty much like we look at the basic and we assume the water in the most simple form. I mean the flow of the water in the most simple form, and such that we can with the time constraint we have, we can finish this topic within reasonable amount of time, and we will just focus on the geotechnical applications. So the two main geotechnical applications we try to achieve here for this lecture is, first, we were able to calculate all the heads that we talk about, the total head, elevation heads, and potential heads. So this is one of the key thing we try to achieve for this Geotech 101 class. Secondly, we will try to achieve how to characterize the hydraulic conductivity of soil. So those two main objectives are the major work scope for us geotechnical engineers. Oftentimes, we work with other branches within civil engineering. We work with the water resources engineers, but what they will need from us, what like a geotechnical engineering get paid for, uh, coming up with the K values, which is the hydraulic conductivity of the soils. They will rely on us to provide the soil informations, and also we need to calculate all the heads. At the end of the day, those heads, especially the potential head, will help us to find the water pressure, which is very important for geotechnical engineers. Okay, the concept of energy. The concept of energy can help us to explain the groundwater flow. So for examples, when we have a geotech structure, for example, maybe a levees or a dam, when we have upstream and downstream. So the upstream representing the higher energy, where you have a higher potentials because of the higher groundwater table. And the high energy will move to the lower energy, where you have a lower water table representing um, the flow of the directions of water where its water goes to. So the concept of energy can be represented by a unit length, which means the total energy can be represented by some form of length units like meters or feet, or we call it as a head. So the head, unit of a unit length represent the amount of energy, and the total energy is made up with a couple parts. First, we include the elevations part, the elevation head. So the total head come up with the elevation head and also the potential head. Or this can be called with the pore water pressure head. It also has another kinetic terms. So it has the kinetic head. Plus whatever remained or whatever extra. So the extra head, for example, can be the chemical terms, can be the temperature terms, also can be electromagnetic terms. And those are much more complicated, is out of the scope of this class. And in fact, those extra terms compared with the elevations and potential heads, this terms is insignificant. So for our geotechnical applications, we can assume this terms to be zero. Furthermore, under static conditions, the groundwater systems, we assume the water move very slowly and sometimes even at static conditions. In that case, which means the kinetic terms is much smaller than the potential terms. So the kinetic head is much smaller than the potential head. For that case, our total head calculations can be further simplified into just two terms. So the total head can be represented by the metric head, or the metric measurements. That's how we measure the heads in the field. So the total head here can be reduced into just two terms, which is the elevations and the potentials. So the elevation head we used to use a simple form of HE, and the potential head we use a form of HP. So the total head in our geotechnical applications will be simplified into this formula. The total head is equal to the elevations plus the pressure head. So the elevation head pretty much is represented by the elevations, straightforward, and the potential head is represented by the pore water pressure divided by the unit weight of water. So this is pore water pressure. And this is the unit weight of water. And unit-wise, it works out this way. So the water pressure, so it's a pressure. So in the units of, for example, under British units, it will be pound per feet square. And the unit weight of water is pound per cubic feet. And if we like work out the units, end up you get the unit of feet. So it's a form of energy now. We represent the energy as a unit length. So we have those two terms, the elevations and pressure heads. And remember, like our energy is relative terms. So for our elevation head, the elevations is relative to the datums. So we talk about datum in the next slides. So pretty much it's a choice of origin of your coordinate system. And for our potential head or the water pressure head, it just depends on the water pressure, which is relative to the atmospheric pressure. So, which means where is the groundwater table? Which means depends on the locations of groundwater table. So GWT stands for the groundwater table. So in our geotechnical applications, we are dealing with very likely we're dealing with the hydrostatic conditions, which means the water tables or the groundwater is not moving or moving very slow. So before we do some examples on all those different heads, let's remind ourselves the difference between the elevations and depth. So for examples, this here we try to set up two different like a datum. So datum locations number 1 and datum locations number 2. So if we are looking at a datum locations number 1, well, first of all, let's also further consider extend these lines, and then so datum number 1 is at point A, and datum number B, datum like number 2 is at point B. And if we do our depth, so this is depth of 0, and assume this is like a point A is like a 3 feet down, 3 feet down, and point B is at a depth of like a 10 feet. So let's try to set up the elevations. So elevation is kind of like a relative terms. So this is at datum number 1. Let's extend these lines. Okay, so speaking of the elevations, if we set up our datums at point A, which means the datum at point A is 0. And it's up to us. In our geotechnical conventions, we will assume going down, going increase with the depth, that is positive. And going the other way, going to the ground surface, that is become more negative. Because in geotech, many times we deal with compressions underneath the ground. So the deeper we go, the geotech convention is become the more positive. So we know point B relative to point A is 37 feet down. So the elevations for datums number 1 at point B is 7. If we go back to the ground surface, which is -3, and we choose like a datum number 2, which is like a datum as point B, then at point B our elevations is 0. And again, moving up, it's become more negative. At point A is 7 feet up, because we know it from the depth. So this is -7 at point A. And at the ground surface, this is -10. This is -10. So what we learned here is we realize the elevations relative terms. Knowing this will help us to find the elevation head later. But like the other important point here is this realize setting up different statums will give us a different like elevations. So one more thing we want to look at here is let's also look at the water pressure. So in geotech, we like the fact that going down is positive. So when we set up like our plots, we like to represent the going down is positive. So oftentimes we will upside down our y-axis because we want to, again, one more time, our geotech conventions, increasing the depth is more like a negative. So let's look at the pore pressure. The pore pressure. So sorry, this is the one more time. This is our depth. So usually we represent it by Z. So this is the depth. And if we look at the pore pressure here, which we use a letter U as a pore pressure. So usually this is our geotech convention. So U means the pore pressure, a small letter U. So if we want to represent the pore pressure in the functions of the depth, we do it this way. We know the groundwater tables. Look at here, and we calculate the water pressure is equals to the unit weight of water times the depth. So right at the groundwater tables, it's 0. There's no water pressure. And after that, our water pressure will increase linearly with the depth, because we know those equations. So the depth is like the water pressure is in a linear relationship with the depth. So this is at a slope of the unit weight of the water because of these equations. And in this case, we can assume above the groundwater tables, you don't have a pore pressure. You don't have a pore pressure. But realize, this is just for your undergrad understanding. In fact, right above the groundwater tables, the water pressure is not 0. In fact, there's a negative pore pressure right there. But anyways, this class is okay to assume this equal to 0. But moving on, if you pick up your graduate study, in fact, we will talk about this more in better details for the CE 566 Geotechnical Engineering number 2, which is a graduate level course. But for this course, we can assume above the groundwater tables, we don't have a water pressure. All right, let's work on examples together on finding all the heads that we mentioned above. So the goal here is to find all heads. Which include the total head, the elevation head, and potential head at any locations. Any locations of this geotech structure. So here is we simplify maybe a site conditions between upstream and downstream, and we simplify maybe down or a site with a saw column here. And then where oftentimes we do this because we want to have a physical model that we can built in the laboratory to simulate the field conditions. So anyways, like this is the laboratory setup over there, and the overall goal here is try to find out the missions here is we need to find out all the heads at any locations. And under the setups, we pick a couple points, point A to point E, and we will try to fill up these tables on the left-hand side. From point A to point E, we find out all the heads, the total heads, the um, the total head, the elevations head, and also the potential head. This is what we try to find out. This is what we try to find out. And remember, we learned those equations together. The total head is equals to the elevation head plus the potential head. For a problem like this, we have a couple recommended procedure. But the very first step we work on is to define the directions of water flow. Remember, we talk about this. You just go from the high energy points to the low energy. So in this case, for this setup, we have an upstream at point E and a lower stream at point A, because the water level at point E is higher than the water level at point A. So we know the water go this way. So we finish our first step. Pretty much is like we defined the water flow based on the elevations of the water tables. Second steps will be define the datums. So this case, the datum is defined for us. After we define the datums, we can find the elevation heads. So we define our datums. Now we have like a point A to point E. So this is the most straightforward. It's the most like a simple steps. The elevation head is always easy to find. Because like once you establish the datums, the elevations will be pretty much just to find out the points you're looking at, how far is from the datums. For example, point A, the point A will be the elevation head will be from the datums to the height of point A. So from point A to datum, you add up all those like a number here, gives you 8 meters. Likewise, point B will be 3 meters. Point C will be 2.5 meters. Point D, very straightforward, 1 meters. And point E will be 12 meters. So we finish the second step. And the third step of the schedule of this like recommended procedure is to put the potential head. So again, what we try to do is we want to find out all the heads at any locations. This case, point A to point E. So we lock down the elevation heads already. Then the next thing to do, we will try to find some potential heads. That's obvious for us to tell. So one of it is we put the potential heads where at the water surface. So when we are open to when we are at the water surface, which means we are open to atmospheric pressure. Of that case, if it's open to atmospheric pressure, then the water pressure is 0. So in this case, on our point A and point E, those are the points that were at the water surface, which means the potential head at point A and point E, they are 0. And once we fill up the potential head, and provided that we also know the elevation head, um, we talk about this, the total head will be to become the sum of the two. So once you know the potential head and also you know the elevation head, you know the total head, which is the elevations plus the potential head. After that, we go to step 4. We will find the total head where there's no loss. So loss means flow through the soil. Because what happens is when the water try to flow through the soil, you experience the resistance from soils. So what I means here is we go, remember in procedure number 1, we define the waterfall, right? So we have defined the waterfall, which is from point E, go to point D, go to point C, go to point B, and eventually you hit point A. So that is the waterfall. So now, looking at this water path from point E to point D, right? There's no loss because it doesn't go through the soil. So from point E to point D, this is what I mean here is there's no loss. And we can find out the total head from point E to point D. So what happened from point E to point D is at point E, we have a total head of 12 meters. This is what we find out. The total head at point E we have 12 meters. And if there's no loss, then the total head will be the same. So at point D, we will also have the same total head of 12 meters because there's no loss. Well, the overall head hasn't been lost, but what happens is the elevations and potential head, they are kind of interchanging. So we also know that the total head is equals to the potential head plus the elevations. So now at point D, you know the total head is 12 meters, and you know the elevations is 1 meters. So knowing the two, you can find out the potential head, which is the total head minus the elevations. So this is 11 meters. So what happens is this is kind of like the conservations of energy. So what happens is point E to point D is overall there's no loss, but there's an exchange of the potential energy and the elevation energy. From point E to point D, we are losing the elevations, but we are gaining the potentials. So that's why from point E to point D, our elevations change from 12 to 1, but we are getting back as a potentials 11 meters. The difference go there. So likewise, So we keep on following the same water path. So from pond E to pond D, we handle that, and from pond D to pond C, and pond C to pond B. So the path within the soils will be a little bit more complicated. So we can handle that later. But what happened is from pond B to pond A are still the same thing. We are step number 4. For pond B to pond A, still the same thing. There's like a no loss because like from the flow from pond B to pond A, you are not traveling through the soil. So there's no loss. So with that, we know that the head, the total head at pond B will be equals to the total head at pond A. And we know that the total head at pond A is 8. So the total head at pond B is also 8 because there's no loss. So we are at step number 4. So step number 4 pretty much just try to take care of these 2 total heads right there. So once we know the total head and also we know the elevation head, then we can find out the potential head, which is the total head minus the elevations. So this is 5. This is 5. This is 5 meters. Okay, now, so pretty much like we get to the most like difficult part now, which is we deal with the locations within the soil body. So which bring us to procedure number 5, where we try to find the total head where location is within the soil. And we do this based on the concept of proportions. Which means here we know that at pond D we have a total head of at pond D we have a total head of 12 meters. And also we know that at pond B we have a total head of 8 meters. And which means like what means here like getting from pond D to pond B, we lost 4 meters out of the total length of 8 meters, because like the distance between pond D and pond B is 8 meters. So the head drops from pond D to pond B is 8 is 4 meters. This is like 12 minus 8, and thus travel through a distance of 8 meters. So if we divide that by 8, which means like here we have 1/2 meter drops. Oops. So what happened here is we have 1/2 meters drops per meter traveled, per 1 meter traveled. So we want to find out the head at pond C, right? So to pond C, we travel 6 meters. So at the end of the day, what does it mean is like we know like according to our calculations here, you drop like 12 meters per 1 meter travel. And we travel 6 meters right here to point C. Then, which means like if to cancel out, we dropped 3 meters. So at point D, we were at like 12 meters. And now, based on the proportions, we know that at point C, it dropped 3 meters according to our calculations here. So 12 meters dropping 3 meters. So which means at point C, now we have 9 meters. So again, the whole thing is based on the concept of proportions, like a linear loss of energy. We can do this because this is a homogeneous soils, isotropic soils. So at the later part of this lecture, we will talk about when you have an isotropic soils, which means like the soil body here now is more than one type of soils. Type of soils means like clay or sand or whatever. So now we only have a standard soils, homogeneous soils. So the soil properties is a constant. So that's why everything drops linearly. So we can take advantage of the proportions. And according to this configurations, we calculated that you would drop half meters per every meters they travel. So if you have like different questions, then like this will change. Then you need to like apply these concepts like to the new problems. You will see the problem in the homework, and also you will see the problems in exams. But you need to understand this concept for proportions. If you need help, come to my office hour. So step number 5 is the most like most difficult part that like you need to handle. So now we know the total head at point C is 9 meters. So with that, we can find out the potential head at point C is 6.5 meters. Again, like this, if you need help here, please come see me during my office hour. So the last part is try to find out the water pressure. So the water pressure is equals to, well, it's better to say this is a small u, not a capital U, because like as the small letter U means the water pressure. So the water pressure, according to the formula, is the potential head times the unit weight of water. We defined this already at the beginning when we tried to define uh, the potential head equals to the water pressure divided by the unit weight of waters. So now we know the potential head, but we try to back calculate the water pressure. So oftentimes we do this like in the field. So we try to do this quick calculations like right, maybe like on site. We go to the levees and or we go to the dams and we are reading some piezometers like measurements. Then we need to calculate the water pressure quickly because like over times maybe there's like an intensive rainfall happens, and you as an entry level engineers, you are sent by your supervisor to to work as a field engineers to go to the field, make some quick measurements, and you need to find the water pressure right on site because you are concerned about the safety of the earth structure, the levees, because like too much rainfall, and then you will make the rise of the water tables upstream, and now you worry about the water pressure is too high that may over topple the dams or the levees. Then you need to make this quick calculations with a clipboard on site. And once you do like a simple calculations, you find out the water head, then you can calculate water pressure, and you can assume, and then like you can make a live you need in order to make that calculations, you can assume the water pressure is about 10 kilonewtons per meter cubes, it should be equals to 9.8 to be more precise. But like quick calculations uh, on the field, then you can assume it's to be 10. So now this is 10 kilonewtons per meter cubes, and now you know the potential head, then you can find out the water pressure quickly. So this is 0 kilopascal at point A, and at point B is 50, and at point C is 65 kilopascal, and at point D will be like 110 kilopascal, and point E, when you go back to the water surface, you don't have any uh, water pressure because it's open to atmospheric pressure. So according to your calculations, point D, you will have the highest amount of water pressure. That may be the locations that you're concerned about, the failure conditions. So here, this is a quick examples for you to demonstrate how to calculate all the heads. Again, for this lecture, we have two main goals we need to achieve. First is calculating all the heads, the total heads, elevation heads, and the pressure heads or the potential head. So once you understand this concept, given a geotech structure, then we should able to calculate all the heads in any location. Okay, Darcy Law. So the picture on the left here show a very good demonstrations on how to measure hydraulic conductivities, which is the K here that we will be talking about for the rest of this lecture. So Darcy Law is set up to is being like a very good theoretical background for us to measure these parameters, the hydraulic conductivities. So this laboratory setup on the left, you will see a soil specimens right here. So we got a soil specimens. We can measure the length of this soil specimens, and this soil specimens is subject to hydraulic head. So on the left-hand side, you have a higher water table, and the right-hand side, you have a relatively lower water table, which give you the gradients in energy, such that you know that the water will flow from the high water tables to the low water tables, from the high energy to the low energy. So this is the basic setup of this like laboratory experiments, and this will help us to define. So with the measure, able to physically measure the delta H and also the length right there, you will help us to define the gradients. And the gradients is equals to the delta H divided by the length. So this is called, actually this is called the hydraulic gradients. So after we're able to measure the hydraulic gradients, we can calculate the velocity, because the velocity of the water flow will be equals to the K times I, which means the flow of the water will be proportional to the gradients. And there's K here again is the hydraulic conductivities. So the V over there is the water discharge velocity, and the K is hydraulic gradients. Oh, sorry, hydraulic conductivities. So which means this will tell you how easy the water is flowing through the soil. Oops. So K is a very important is, well, I put it this way, is the most parameters when it comes to soil hydraulic. And we need to, as a geotech engineers, we spend a lot of effort try to characterize these parameters for the soil we are working on the site. And there's a lot of like a field testing and lab testing is trying to figure out this number. And after we obtain this hydraulic conductivities for our soils on site, then we can use that parameters to do a lot of engineering design. So furthermore, we talk about the velocity, and the velocity, if the discharge velocity is divided by the porosity. So again, n is the porosity. We learn about this interface relations. So the porosity is equals to the volume of void divided by the total volumes. So if we divide the discharge velocity with porosity, then we got the seepage velocity. So seepage velocity means like when because if we just talk about discharge velocity, then pretty much like we are talking about the water going through the soil in a strict path flow. This is a good approximations, but may not be the truly accurate. The true velocity that going through our soils is the one that will migrate through the void. So that's why like if we divide by our velocity uh, with the porosity, then we will get the seepage velocity. And speaking of the hydraulic activities, it can also the K can sometimes like we could express it as coefficients of permeability. So hydraulic activities and coefficients of permeability, we also reference as the K values, and it highly depends on the soil type. So you can imagine like a two extreme case when we have gravel, when water try to like seepage through the gravel, it happens like within seconds. So the hydraulic conductivities or the coefficients of permeability of the K values for gravel is relatively high. So this is under the unit of meter per seconds. So this takes like seconds to travel through gravel. Um, but the other extreme is clay. Right? For clay samples, everything takes times. So if you have like the same thickness of soils on your site, maybe like we talk about 1 meters of soils, you could take uh, uh, really quick to take about minutes to for the gravels to go through 1 meters of soil of gravel. 1 meters of gravel. But you have a 1 meter of clay, then you will be like a million times like slower. Then you will take years to go through 1 meters of clay. So that's a huge difference when you deal with a gravel or clay for the issue of drainage for a project site. So as a geotech engineers, like when you design for what type of material you want to backfill on your soil site for your engineering purpose, it highly depends. Depends on what you want to achieve. If you do want to slow down the water flow, for example, it's like if you have a levee project, or if you have a clay, or if you have landfill project that you need to slow down the water migrations, then you want to have fine grains material as your backfill. But if you have a like a have a at the like a drainage purpose, if you want to like speed up the consolidations or if you like want to detour the water flow, then you will need like coarse grain material, sand or gravel, to allow the water pass through your project site. So this concept is important for geotech engineering. It's also for civil engineers to think of what type of materials they need to handle or they need to design for. Okay, let's talk about Darcy Law. So one more time, it's the simple experimental setup here. Given that you have a soil specimens working on, and this soil specimens has an area that go into the page. So if you imagine you have a 3D specimens instead of 2D, so you have an area going into the page, and you also have water hydraulic gradients that give you a water head to drive the water past through the soil samples. And we assume this is a 100 a saturated clean sand samples. So everything is only flow through laminar flow. So if we talk about Darcy Law, first of all, we need to be clear about the terminology. So we used to use the capital Q to describe the amount of water flow. And this is in the unit of volume. And when we used to when you use like a smaller Q, we used to describe this as the flow rate. So which means the volume divided by time. So the units will be, for examples, will be meter cube per minute. And according to the Darcy Law Darcy experiments, we realize that the flow rate is proportional to the area. So the larger the area, the more faster the water pass through, and the Q also the flow rate is proportional to the hydraulic gradients. So the higher the water head difference, the quicker the water pass through the soils. And also we realize the flow rate is indirectly proportional to the length of the soil samples. So the longer the soil samples you have, then the more times that well, the longer the soil sample is, the rate will be much slower. So the shorter the sample it is, the quicker the water flow rate will be. And we want to measure okay, we want to measure the hydraulic conductivities or the coefficients of permeability, and we take advantage of the three observations we talked about. So realize the flow rate will be proportional to the three items we talk about: the area, the hydraulic gradients, and also indirectly proportional to the length of the soil samples. So end up if we can measure these three terms, then we can find out the soil specific parameters. K over here will be a constant, will be the constant between the three physical terms that we can measure, and also the flow rate. So this is the Darcy Law. And if we reorganize these equations, the delta H over L is the gradients we talked about in the previous slide, and equals to the area. So Q equal KIA is the Darcy Law. All right, a quick examples on using the Darcy equations. A simple setup here again. Now we can measure all the physical parameters that is easy to measure in the laboratory. So first of all is the flow rate. The Q is equals to 1.38 times 10 to the negative 5 meter cube per seconds. And also we can measure, very straightforward, measure the H1 and H2, which is the water table from upstream and downstream. And also we can measure the area of our soil samples there, and also we can measure the length of the soil samples. And what we try to achieve is find K, the hydraulic conductivities of the soils that we put a head difference there, so water can flow through it. Then we can hopefully we can indirectly measure the K values. We know the Darcy Law is equals to KIA, and the I is delta H divided by L times the area. And we want to find K, so we can reorganize equations. So the area is capital A. Then we can plug in the informations. Every time when we do any calculations, no matter how simple is it, I recommend you always put down the units. Times 2 meters divided by the delta H here is 2.8 minus 2.64 meters, and then times the area, which is 0.025 meters squared. And you solve for this math here, and then you get the K is equals to 10.69 times 10 to the negative 4 meter per seconds. So with the indirect, so we want to find out the K values, and with the direct measurements, we can indirectly calculate K, the hydraulic conductivities of the soil. Okay, now we get to another topic, which is anisotropic. Okay, now we get to another topic, the anisotropy in hydraulic conductivities. So now we step up the compressibility into another level when we have soil samples, or we tried what we're trying to doing here is try to simulate more realistic ground scenario that the soil site that we have is always is not just one type of soil. It's not homogeneous ground, but we always have different type of soils, and for a project site. And now, what we're trying to do in the laboratory now is try to simulate when you have different layers of soils. What can we do to try to find the equivalent hydraulic conductivities? So the main purpose here is find the equivalent hydraulic conductivities, which means the soils that we deal with now is no longer isotropic. So if we only have one type of soils, which is homogeneous, the Darcy Law allow us to find out the hydraulic conductivities at the end of the day with some simple measurements. But when we have two soils, layers right here. So given this example here, we have a sand and we have a silt layer that require a little bit more work in order to find out the hydraulic conductivities, what we call now as the equivalent hydraulic conductivities that can represent the system that has more than one type of soils. And we have two cases to deal with. We are looking at the first case. Now, the directions of the flow of the water is parallel to the bedding. So when we say the bedding, this is the bedding. So the bedding between the two type of soils. And we know the flow of the water goes this way. So that's why the flow of water here is parallel to the bedding of the soil layers. So that's what we try to achieve. Find a hydraulic connectivities that are equivalent to the whole systems. Okay, some simple setup. First of all, under this experiments, so each type of soils it has a thickness H1 and H2 right there, and the length of the soil is the same because that's the way that like we control in our laboratory, and we assumed we have a unit length that go into the page. So when we think about the area of the whole setup, uh, this dimension is equal to 1. So the area for the sand here will be H1 times 1, and the area for the silt layer is H2 times 1. So area 1 will be equals to H1 times 1, and area 2 will be equals to H2 times 2. And realize that there's a head drops across like this setup, and the head drops here now when the water flow through the systems, the head droppers will go down linearly. So we expect the delta H will go down this way. With at the way at the upstream, the delta H, which now is a function of the travel distance, will be equals to the total head drops. So we have a total head drops right there. And when the water exceeds the soil's system there, the head drops depends on the length again. It will be 0. And by the times that we exceed the soil layers, the total amount of flow. So we talk about when we exceed this like soil systems, the total amount of flow will be equals to Q1 plus Q2. So you imagine like there's some water come out from the sand layers, and also there's some waters come out from the silt layer, and the total water that comes out from the systems will be equals to Q1 divided by Q2. Okay, now we try to set up our equations. Eventually, our final product should able us to find out what is the equivalence K. That's what we want to get to. So first, let's look at the total amount of fold, and if we use the Darcy Law, the total amount of flow will be equals to the equivalence K that representing the whole systems times the head drops divided by L. So KIA, so this is the gradients terms, and then times the total area. So we look at the whole thing as a systems. That will be equations 1. And if we break it down into different type of soils, then the Q1 at the sand layers will be equals to K1. So we have Q1 going this way and Q2 going the other way. And we have a K1 representing the sand layers and a K2 representing the silt layer. So Q1 will be equals to K1 times the delta H divided by L times A1. Oops, this is multiplied. And Q2 will be equals to the hydraulic conductivities of the silt layer times the delta H divided by L. So we have this, pretty much we have the same head drops. So that's why the delta H is a constant. And then the area of 2. And we know the total amount of flow will be equals to Q1 plus Q2. So if we from these equations, we can represent this so like this, because we know like Q1 and Q2, so we can combine them with these equations. And let's call this equations 2. And now let's do some math here. So from equations 2, if I divide the whole thing with the total area and then multiply back, so pretty much like mathematically, uh, that's the same. So mathematically, I can divide the whole thing with total area, but multiply it back. So just like multiplying the whole thing by 1. And the next things, if I reorganize the equations, so let's divide the total area inside our equations. And this gives me equation 4. So if we compare equation 1 and equation 4, we realize that this part, let me set the color. We realize that this part is the same, and this part pretty much is the same. So we achieve our goal that the equivalence K, in fact, is equals to K1 times A1 divided by the total area, and plus K2 divided by A2 divided by the total area. And if we factor out the total area, we have K1 A1 plus K2 A2. And knowing the area is equals to H1 times 1, then we can find out the K equivalence as a normalized terms that we have a unit length into the page. So this becomes the A1 become H1 because the A1 is H1 times 1 plus K2 H2. So we kind of like what we try to do here is we simplify our 3D problems into our 2D problems, and we will find out the equivalence K is equal to these equations. So that's just 2 layers. Okay, second case of anisotropy hydraulic conductivities. Now, this is the case that the water flow is across or perpendicular to the bedding. So what is a soil bedding? Soil bedding is the layers between two interface. So you have a sand and silt layer now. So this is the soil bedding, and this is the flow of water. So it's kind of like a perpendicular or across the soil bedding. So like unlike the other one, it is parallel with the soil bedding. So again, this is kind of like a parallel to the bedding right there. But this one now is we have a scenario that the flow of water is across or perpendicular to the bedding. So in geotech design, either case can happen. So you can imagine that like for case 1, when the water flow is parallel to the bedding, it's more like a lateral soil. When you have like a lateral deposit of soils that layers up on top of layers, and then the water is going horizontally across parallel to the bedding. But in some design, in some geotech design, we want to control uh, the water flow that go across the bedding. And which next examples, like we will highlight like some of the landfill design, we mimically, we purposely make that happens that the water flow go perpendicular, go across uh, to the bedding of the soil. So um, again, like the same thing, the main goal here now is try to find um, the equivalence hydraulic activities, right? Just like the previous slide, what we try to achieve here is try to find the equivalence hydraulic conductivity for the whole setup, So and some a little bit more like a similar background here, where for example, like let's say this is not restrict to this is a equal distance. Like we have a length 1 and length 2 right there. But meanwhile, it's like we keep the area the same. So the height here and height there is the same. So H1 will be equals to H2, but the length can be different. And if we reimagine like when you impose a water head, which means like difference of water level going in and going out, so which gives you a delta H right there. This does like a change of head, will be unlike case one that you go like constant slope that like going down. But what being different now, the head drops highly depends on the type of soils that we're going through. And you have a sand layer and you have a silt layer. And also we could like imagine that sand versus silt, and silt will be the one that more likely like carry most of the energy, because like a sand the water can drain through the sand like a much more easier than like when you drain through the silt layer. You would take like a much longer times for the water try to travel through the silt than the sand. So what happens end up is like at the beginnings you still have delta H. You still have like before entering your soil systems, you still have all the head difference at the beginning. But when it goes out the systems, all the heads are gone. But whatever in between is not a linear relationships. It depends on the type of the soils. And from the jobs from the sand to the silt layer, maybe just tiny a little bit. Let's just go down a little bit from the loss of the energy loss in the sand when you compare to the silt. And most of the head drops will happens at the silt. So this is the observations that we have in terms of the head drops. In this case, the total head drops that we talk about here now, so the total head drops will be equals to the head drop at 1 plus the head drops at 2. So at this point, we drop delta H1, and then like at the end, like when we like go down, exceeding the silt number 2, then we drop the amount of delta H2, and the two add up together will be equals to the total head. And the amount of fold we're going through now will be equals to Q1 plus Q2. So the rate is the same. I'm sorry, it's not plus, it's equals. So the rate is the same throughout the whole cycle setup. So the total amount of flow pretty much is like the same throughout these two soils like sections. So first of all, well, again, at the end of the day, we should be able to find out this KEQ, the equivalence gauge for systems. So first of all, for each type of soils, if we set up our equations, the QI will be equals to KI times the delta head drops times LI times the area. Area is constant. And we know that each Q will be equals to the total flow rate. And from these equations right there, if we reorganize this to solve for delta HI, will be equals to the Q times, so the Q is a constant now, KI and A. And in total, if we sum up all the change of head drops, will be equals to Q divided by A, which is the constants that we factor out, and the summations of all the variables. So this is equations 1. This is the summations. And for the Darcy Law, apply for the systems, my Q equals here now is equals to K equivalence, I and A, and the gradients is equals to the sum of all the head drops divided by the total length times the area, which is a constant. So this is equations 2. So we substitute equation 1 to equations 2. So which means we try to substitute this part into this part. So we substitute like equation 1 to equations 2. Then we got this equations. Q is equals to equivalence K, and then pretty much like just substitute equation 1 from equations 2 there. Then this is divided by the total length and times the area. So if we realize these equations, there's some terms that we can cancel out. The Q terms are gone, the area terms are gone. And if we do our math now, the KEQ will be equals to the total length divided by the summations of LI divided by KI. So we solve for what we need. Find out the equivalence K, find out the equivalence K for the systems. So next slide, let's work on examples together. So this is kind of like real-world problems that like in the landfill business, when we try to design for the what we call the clay liners for our landfill project. So what happens here now is this part is your Geotech Design. So pretty much like you need to select the material or select the combinations of a material that allows you to prevent your wastewater. So you have a lot of wastewater here. So this part is your wastewater. You need to design an earth structure that prevents the wastewater going down into the groundwater. So this is the groundwater, because you don't want like our groundwater systems getting polluted by the waste, and like the waste will end up like generate like wastewater, or we call the leachate. So leachate is the wastewater from the municipal waste that like you kind of like harmful and dangerous, like toxic, all the bad thing happen together, and you want to help those like a wastewater stay out from the groundwater. So our geotech design is based on understanding on like a soil behavior, hydraulic behavior. We want to find a combinations of like man-made materials and also natural materials that like can do the job, that slow down, or you better like if not like totally like block out the water, but at least slow down the seepage of the water. Because like we when we set up, or when we like design for a landfill, it will be stayed there for hundreds of years. So it's almost like impossible to like totally block out, but at least like based on our engineering like a procedure or engineering understanding, we can design for within the lifespan of the landfill sites. Could be like last for 1,000 years, or like 500 years. Uh, that like the wastewater will not go into the groundwater. If you're like if you think like you can create a systems that totally block out the whole thing, it's almost like economically impossible. But like if we understand the earth material, which is soil well enough, we can do the job. We can do the jobs. So when we see a problem like this, well, like for the design, what being important at the end of the day is find out the equivalence K. You want to know like from this geotech design, what is the hydraulic conductivities, not just one layers or not just one soils, but like for your whole design, uh, for the whole systems, how you work together. So which is uh, the concept, which forms the concept of equivalence hydraulic conductivities. So now we have different types of materials, and if you look at a geotech design now, now it's given to you, but your jobs now is just try to find out the equivalence of K. So if you look at this like a design now, you have the geotextile filters, and then like on top of a sand layers, and then on top of like a very thin, what we call the geomembrane, pretty much is a plastic layer. Um, and the thickness of this layer given to you is like a 30 mil. And like a 30 mils, uh, 30 mils, in fact, is equals to 0.0762 centimeters. So it's very, very small, very thin layers. It's kind of like a plastic layer that you can wrap around the soil. So this is 30 mils, and the hydraulic conductivities for these layers is 10 to negative 11 centimeter per second. So this is the hydraulic conductivities for that plastic material. And for the sand layers, I forgot about to mention, the hydraulic conductivities will be 10 to negative 4 centimeter per second. And sandwich them is again the same sand layers. So this is 10 to negative 4 again. And then you will be another like a wrap with another like a 10 to negative 4 11 centimeter per second of geomembranes material, the same thickness. And the second layers of the geomembranes will be on top of a very thick clay layers. So we know clay. Clay is a compacted clay. This all is about you will relate to constructions. So you will design how the whole thing to be built, and like you want compacted clay to your as kind of like a last defense when you get into the groundwater. So this is the groundwater. Uh, and the hydraulic conductivities of this clay layer is 10 to negative 7 centimeter per second. and, um, and this is 91 centimeters, 3 feet thick of compacted clay layers. So this is just kind of like just an example design. And like in the business of landfill, they will like look at the cost and also look at the construction schedules, and they also look at the available materials and come with different combinations of design of a geotech clay lines. So and you realize like the geomembrane are nice because like those are plastic. You have a very like a low hydraulic conductivities, but also you realize they're very thin. So if you punch a holes like within like that plastic wrap, pretty much like you lose the whole difference. You lose the functions of the systems. But anyways, like this is the geotech design, and our job now is try to find the Griffin's key. And remember, like on the previous slides, we talk about like those equivalence case, and based on different scenario, case one and case two, you will end up have different equations at the end. So the very first job you do is you need to think of what type of scenario is it. Is it like a parallel to the beddings, or is that like across the bedding? That will make a difference. So you realize the water that you have now is right here, and you want to go down this way. So according to this like the scenario, the directions of the water is across all the bedding, because the bedding is those like interface layer between like a different type of soils. So pretty much this times you are across or parallel to bedding. And the equations for that is equals to the summations of the thickness divided by the individuals, the summations of individuals like length divided by the hydraulic conductivities. So which is this equations here, because this is under the concept of causing the bedding, and we prove it like how to come up with these equations. So now you have all this informations. And your equivalence K is you need to consider all these different soil layers. First, you have the sand. You have your sand layers to start with. The thickness of this, and the thickness of this. The bottom part is the thickness of this, and then divided by hydraulic conductivities. So this is your first sand layers, and then like you will have your geomembranes layers. Underneath your sand layers. And now this is like a very thin, and also come up with very low hydraulic conductivities. So I highly recommend you always list out all the units. Oops. So, and then you have another like a sand layers right there. And then on top of the geomembranes layers. And lastly is your clay layers, which is 91 centimeters. So this is how we find out the equivalence K. And we will solve for these equations, then this is our final answer. So this number here represents the hydraulic conductivity's performance for the whole setups. which is the Geotech Design that you have now. Okay, I hope like this two scenario, this two case will make sense to you. And like if you have any questions, I highly recommend you to come see me during my office hour. Okay, last but not least, I just want to introduce you some like existing hydraulic conductivity correlations, because you realize like this like hydraulic conductivities could be very expensive and hard to characterize based on laboratory testing and field testing. So in the past, there's a research has been done on trying to estimate this hydraulic conductivities by using some correlations. And those correlations, first of all, think of like what type of soil parameters or soil characteristics is related to. So uh, research on like the theoretical background or the theoretic frameworks tell us the hydraulic conductivities depends on the soil skeletons and also depends on the fluid type. And uh, the basic work form is like this is the fluid part and this is the soil skeletons. So hydraulic conductivity is pretty much just based on those two parts. And there's some more existing correlations that are being like available, when you're practicing in the future, if you are sort of budget, you don't have the money to do the lab testing, and you don't need to have the money to do the field testing. Field testing are very expensive, but that is a better way to do it. Actually, it's better than the lab testing. So when you take this C368 class, then we will spend more time in the laboratory to talk about the shortcoming of or the limitations that exist for the laboratory characterizations of hydraulic conductivities. But anyways, if there's no field test, there's no lab tests available, then you may want to look at some like a correlations to help you to characterize the K values. But remember, like don't lose the big picture. When we talk about hydraulic conductivities, if you know about like your soil type, or if your soil type is kind of like common soils, then you have the ballpark answer. Gravel, you have a typical range to start with. Sand, you have a typical range to start with, and also like the clay. But very likely, your soils on the project site very likely is a mix of like many different like type of soils, gravel, sand, and clay, and so those correlations may help you to base on the parameters that you know, for example, the void ratios of the soils, and also some more like sophisticated parameters as zero over here, which is depends on the specific surface area of soils times the G sub S and times the unit weight of water. Um, that may help you to plug in the equations. That may help you to baseline or to ballpark your hydraulic conductivities. And there's also somewhere much simpler simple like correlations that being available, which is the hydraulic conductivities is directly related to the square of D10. So remember, like once you have we talked about D10 in the previous lecture 2. So D10 is the diameter of soils at 10% passing. Or you can find that out from the grain size distribution curve. So one researcher over say this is Hazen's 1911. This it depends on D10s, but there could be some other correlations. Say this is like it depends on D15. So when you use those correlations, you need to be very careful. You're very careful. Understand this. This is just able to give you a ballpark answer. If you want to have a very accurate hydraulic conductivities to use for a project, where likely like someone maybe need to do a numerical modeling work for the groundwater flow, then like this may not be sufficient. If you have a very like a serious or you have a very expensive project, you better do something like a field testing. But last but not least, if you want to have some quick ballpark answer, those correlations may be helpful. All right, this is the end of lecture 3, and I highly recommend you like make good use of my office hour, because like starting on this lecture, we go through some concept that uh, may not be as obvious as like the previous two lecture. So if you need any help, please come to my office hour. All right, thank you. Bye bye.